Hello, everybody. It's amazing to be here again at Camera Image, and I will talk a little bit about a subject I haven't talked about that much because I'm not an expert in that topic, and that is machine learning, or how I phrase the title, using trained algorithm in interactive color grading. Yeah, and so this will be the first half of that session. So there is an emerging technology which allows us to do all sorts of interesting stuff with motion picture, and that technology, as I said already, is machine learning. And I want to critically also show and demonstrate and evaluate together with you today what we can do today and what we cannot do today, and what we might be able to do in the near future. But please don't quote me in 3 years' time. This is a really tough topic to do any predictions on. So this is just like based on the current states of affairs. So don't quote me in 3 years. I think it's interesting and also valuable to understand why we have. Yeah, but at some point I probably need another microphone when it comes to the live demonstration. Okay, so why do we see this rapid explosion in the field of machine learning now and not 10 years or 20 years ago or in 50 years? And the reason for that is that we were lucky in the last decade. We did some major theoretical ideas early on, 50 years ago, with backpropagation. That was in the 1970s, but we will see just in the next slide that it's not only about the theoretical ideas, but we had some really groundbreaking breakthroughs. In 2014, I picked just a few of those, the concept of dropouts, and then in 2015, the concept of residual learning, where we not trying to make a model learn all the stuff in one go, but rather let it learn the residuals, the differences. And that allowed us to scale up these models immensely. Before that, we had all sorts of issues when I say we, I exclude myself because I'm not a machine learning researcher, but we as a society. Scaling up those models would not lead to better algorithms. But then these key breakthroughs, especially residual learning, the skip connections, really made all this difference. And this is a pretty simple. So these were very simple concepts, and that made all of the difference. And then maybe the most influential paper was Attention is All You Need from Google, where they introduced the concept of attention. And then the resulting architecture transformers is basically now everywhere and enables so much of what we see today. And basically thank you. So should I switch? Should we try? Where is it? Thanks. 1, 2, 2, 2. 1, 2, 2, 2, 2. A big applause for the Camera Image technical team. I think I've been here for 9 years, and these guys are just amazing. So they deserve that applause. So, and what we're doing since then, since 2017, is basically collecting the merits of these breakthroughs. And we haven't had any further breakthrough really in the deep fundamental concepts. There was one paper from OpenAI, scaling laws of natural language models, where they try to mathematically predict that now we can scale up the models, and we will improve the models by just scaling it up. And we basically see since 2020 that scale is all you need is kind of dominating the field. So we doing bigger and bigger models. But not only theoretical concepts are important, but the timing needs to be right. And the timing seemed to be right since the last decade, because we have a few things which are crucial for machine learning to progress available. For example, sharing is caring, and we share a lot with in social media and everywhere. So we put everything we know, we see, all of the ideas in the open public domain. And this sharing that information is an enabler for machine learning algorithms. Also on the computation side of things, we have cloud computing, larger GPUs become available, that really enables us to actually really perform those training and operations. And then on the other side, sharing the learned lesson is really pushed by a strong trend of open sourcing especially in the IT and software fields. These are all the ingredients for this boiling soup of innovation. And like in a chemical reaction, we are in an exponential growth at the moment. So to visualize this here, I have show you a plot of published papers on Archive. Archive is an open source platform or service which hosts freely available scholarly articles. And if you look at the papers published per month that are using or discussing machine learning, we see this exponential growth. So in 2007, maybe I show this here, we were about to have 10 papers per month published about machine learning. Then roughly 6 years later, here somewhere in the middle, we went up to 100 papers per month. And then another 6 years later, roughly, we have 1,000 papers per month. So we can see that every 6 years we get a 10x of increase of research published on the subject of machine learning. We could also look at other statistics, for example, GitHub projects that utilize machine learning. And we see a similar trend where in 2019, we hit the 500,000 projects on GitHub that has to do with machine learning. 2 years later, we cracked the 1 million, and then 2 years later, we are cracking the 2 million projects on GitHub. So every 2 years, we double the amount of projects available on GitHub. The same trend you can see if we look at computation required to train a model. So here you can see, oh, this looks like a linear trend, but be careful, here the scale on the y-axis is a logarithmic scale. That means a line on a plot where one axis is logarithmic makes a linear line be equal to exponential growth. So the amount of computation to actually train those models also increases exponentially. I think it's clear also that the costs that are required to do that training also scale exponentially. Where in around 2018-19, you would be able to train something with the money of, or like the worth of $10,000 of GPU processing. 2 years later, we are at $1 million, and again, 2 years later, we are at $100 million. So it's every 2 years we have 100x in costs. It's a little bit mind-boggling, but yeah, this is where we are. We also see that kind of trend in number of foundation models. More and more people are working on foundation models. But you can also see other aspects, and this is an interesting one. You can see, you can look at patents granted that are relating to machine learning, and we can see that every year, almost roughly, we see a doubling in the patents granted that have machine learning as a subject. Also interesting is if we see this trend everywhere, if we split this up in regions, so we have here China, European Union, and the United States, and the y-axis is lined up so you can compare them, but we can see an exponential growth in all of them, while some are more advanced than the others. So okay, now let's get a little bit into a little bit more. Into what machine learning is, and we start with a definition, as always. And this is the vanilla definition of Wikipedia, which I find quite good. The use and development of computer systems that can learn and adapt without following explicit instructions by algorithms and using algorithms and statistical models to analyze and draw inference from pattern in data. What is important here are, I think, 2 or 3 main things. The one is it analyzes the pattern in data. So instead of talking about the patterns, we need to talk about the instead of talking or thinking about the data itself, we need to think about the patterns that whole data pool provides. And then these machine learning algorithms, they don't follow explicit instructions. So there's not you don't need to sit down on a computer and write every individual step of that process you want to achieve yourself, but you take the data, which provides the pattern, and and then we use statistical models to come to a conclusion or to a function. And this should sound familiar to you if you think about, we do something similar, or we have done something similar in the field of color grading already for quite a while. You might think, what is it? And if you think a little bit, then yeah, you're right. It is the film look. So the print film emulation is kind of a similar approach, because if you want to basically replicate what something does, for example, a film lab, you have two choices. The one is you write a simulation. A simulation, by definition, is models that simulation models, they model internal states to replicate external behavior. So a simulation of a film lab would be, you sit down and you write basically a model that describes and computes all the chemical interactions that's actually happening in a film lab. That is quite complex because, yeah, you need to, first of all, you need to know what's going on in that model, so you need to know all of the different states and how they transform from one to another. Or a much easier way is you send 4096 patches through that process, and you look at the data and the patterns in the data, and you build up an emulation. And an emulation mimics the external behavior without replicating the internal state. So a print film emulation does not tell us anything about what's going on in a film lab. We don't know, but we don't care, because what we have is that emulator, which is a black box for us, which does basically the thing we want to do. And in a way, machine learning is basically an emulator. So instead of calling it artificial intelligence, which is a very stupid term in my view, or even machine learning, we could call it a function emulator, because you give it some data and you describe what you want to learn by the way you define the cost functions. And then you choose a suitable model which is expressive and enough to do what you want. And then you via backpropagation and training, you let that technique figure out a suitable emulator for you. So this approach of, instead of simulating but emulating stuff, in our industry, in the motion picture, we saw over the last years basically two fields where this was applied. On the one side, we have computer vision algorithms, which are there for a long time, and which were traditionally coded up by really a programmer, programming exactly how a tracking works and how you compare contrast edges or gradients and do like tracking and all of that. And on the other side, we have computer-generated imagery. For example, if you want to render a scene, a computer-generated imagery with simulation, you need to first model objects in a simulated scene. You need to set lights, and then you have a ray tracing algorithm, which is a simulation, which basically goes down and counts all of the photons that interact with each other, and then this generates the final image. So a classical CG generated imagery is a simulation of the real world. If you use machine learning to generate images, you get also a Utah teapot. But you don't have a scene, you don't have a light, you basically skip all of that process the same way you skip simulating the film lab when you apply a print film emulation. Yeah, so computer vision and computer-generated imagery. And I want to talk mainly about the computer vision side of things. Examples for computer vision algorithms that nowadays use these emulation techniques is, for example, object detection, object segmentation, semantic metadata, knowledge graphs, action detection, similarity. So you say like, oh, I have an image, show me or find similar images. Also depth estimation, normal estimation, pose estimation, reflection, shading estimation. These are examples of computer vision algorithms that now become available or achievable because we have this new technique. They are typically fast, interactive, and provide utility. On the other side, we have machine learning-powered computer-generated imagery. Mainly diffusion-based models are used for that, and examples are text-to-image, in painting, image-to-image, text-to-video, image-to-video algorithms here. So I made us a small table to comparing the two main fields or main classes of algorithms, because I think it's a good way of grouping those algorithms because they share similar behavior. So computer vision algorithms that are infused by emulation or training, machine learning, they try to gain understanding or meaning. So they try to make a computer see something which is very obvious to us. This is a cat, this is a dog, this is a face, for example. On the other hand, computer-generated imagery or CGI with machine learning infused, it's more like a predictive or a generative nature. So it tries to predict a missing part of an image. So you leave out a patch and you let it fill in that patch, or you say like, what is the next word in a sentence, for example. These are in nature more predictive, and they generate stuff. The computer vision algorithms, they are set up to be analytical and really deterministic. That means that similar input will produce similar output. So because that's what we want. We want to basically that the output really closely correlates with the input. We don't want that a car suddenly is 100 meters away, and in the next moment it's 1 meter away. Yeah, that would be not good. On the other hand, the CGI algorithms, they are, I call them pseudo-stochastic, because under the hood, it's a computer, it's deterministic. But what I'm trying to say with that is that they are highly chaotic in their behavior. That means a small change in the input will produce a completely different output. So that's why when you change the seed, when you increment the seed of one of those models by 1, you will get a completely different image. And that's so severe that they're adding basically other stuff like control nets and other things to kind of get hold onto that. Computer vision algorithms are good known to be good in interpolation. So if you see one cat and one dog, or a few, and you see an unseen cat or dog, then it will interpolate between the labels and the examples. But if you show it, if you want to see a hamster, it will not be really good at that. The CGI algorithms, they are also explored in the way of extrapolating the results. Computer vision algorithms, they attribute utility. So we think that they, in general, they provide utility, especially in our industry for the creatives. And the CGI imagery, this is where the current hype attributes agency, or we do a lot of anthropomorphization. It's a terrible word, but it really describes really good what the problem is with that. If we think about human traits, so we attribute human traits or emotion or intentions to non-human entities. That's the definition of that word. I put it down here as well. And computer vision algorithms, they are well established. So you interact with them probably mostly every time you use your mobile phone. And the CGI ones are the one that are currently that hype that we all know about. I don't go into it. But the CGI, the machine learning powered CGI algorithms, they are basically models, again, so we know this now, they are emulators. They mimic the patterns found in the training data. And that leads, in this context, to quite a few challenges we need to first address before we can really safely use them. Diffusion models vary dramatically in image quality. I have here two different algorithms produce an image with exactly the same prompt, a woman with curly red hair standing in the forest, no text. And we can see almost intuitively that with which kind of data those two models were trained. If you zoom in, you will see DCT compression artifacts that you normally see from JPEG or XDCAM material in the output. So because that model never saw curly red hair without JPEG compression, it doesn't think anything. It infers. It basically concludes that that is the property of curly red hair, basically JPEG compression. And also when we look at the mood of the colors, you can, because I tried not to give any kind of instructions in terms of the color, so we will see a kind of the normal distribution of that data set that those were trained on. When we can see here more video-ish colors that are probably gamut clip, we see some highlight clipping on even in the hairs here, because probably that is the pattern in the data that model was trained on. And on the other side, we see basically muted colors, different types of shading on the skin tones, and that reflect the overall pattern in the data that was trained on. And no models are trained on scene-referred data, which is also a technical problem, because it doesn't know anything. Well, it's not knowing. I should stop my, okay. It has never been confronted with scene-referred data, so it will only produce what it basically saw. So we have no models that really produce scene-referred data. And then there's also some ethical and legal challenges, because if there is bias in the training data, there will be also exactly the same bias. If there's a pattern, there will be also bias in the output of that model. So there's a lot of things we still need to figure out, I believe. And also what we see is that these techniques are typically used in more in visual effects and not in interactive color grading. Because my talk is about interactive color grading. I don't want to say anything about those technologies in other contexts, and I see those, or we see those techniques used more and more in visual effects, because typically this also means like it's not only one tool you work, but you chain different tools together. So you have one model that does one thing, another model that does another thing, and this is typically, and a lot of iterations, and this is typically also how visual effects work. And so we see that, yeah, these things are more used in visual effects and not in interactive color grading. But a good note is we see that those projects also require more grading, because the stability over time and also the labor-intensive nature of that process makes it quite effective to actually do the final tweaking of the colors in a real-time system. So similar to heavy visual effects movies, content that is generated that way requires more grading and not less. And also there's a practicality, so which distinguishes the visual effects in a grading room. If you ask a colorist, how much time do you have to finish a shot, then typically the answer is until the director or TP gets bored. And in visual effects, you hear something like, oh, anywhere between 3 minutes and 7 months. So the time scales are just like very different, and we see still this bulky CGI-generated technology, or any bulky technology, first be deployed in visual effects, and as they become more robust, more interactive, more near real-time, they slowly diffuse into the real-time arena of finishing. And also, I think that's one of my last slides before we actually look at some things. We also need to acknowledge that we are not in the center of all of that. I mean the motion picture industry. Because we have two main drivers in this innovation, boiling soup of innovation. On the one side, we have the academia, and they are interested in research, working on core architectures, working on the components, trying to get the next big breakthrough. And on the other side, we have the big corporations that are interested in robotics, autonomous systems, surveillance, big data analysis. And if they look into content creation, then it's typically for the content creator market, which might have also different requirements for fine, high-quality details like we do in the high-end motion picture industry. All right, so let's have a look at some examples. We go from easy to difficult. So one thing which is which is already in FilmLight for a year now, which utilizes machine learning in the field of computer vision, is face tracking. We believe this gives a great utility to the colorists, because the colorists focus a lot of attention to the faces, because they are our gray cards in terms of how we perceive colors and also stories. So when a colorist works, she or he really focus a lot of work on the face. And having just an algorithm which reduces the task of like propagating a correction over time, then that is useful. And with this technology, we also can make new interactions with those objects. For example, if I add a layer and a shape, and I attach that shape to the tracker, what we now can do is also we can unwrap the face, and because we have an idea of the object, what we can do a UV unmapping, and that allows us to draw the shape and also define the shape in the UV space where the X and Y coordinates are the X and Y coordinates on the object itself. So instead of X, Y on the image, we go X, Y on the actual object we are working on. That's nice because this also allows us to do taking standard things like feathering. So if I'm just opening that, and if I feather the face, but in the UV coordinate, instead of feathering it flat like this, we will feather it along the object's skull, because that's basically the so we can take now algorithms which we already use for a long time, like feathering. It's a very simple algorithm, but now with machine learning power, we can now bring it to other areas here. So we can see that that can provide great utility to a colorist. So that's object tracking. And then another thing which becomes slowly kind of available is depth mapping. So taking a 2D image and generating basically a black and white image that resembles the depths. And I can here, there's one of the first models that were openly available in 2020, like 4 years ago, and which were also deployed very quickly in some consumer products, and is a depth map called is called Midas. That's the name of the model. So what I will do now is I will have 2 cursors up here, and the second one we will look at the depth channel. And so now we can compare, or we can have a look at the image and then the depth channel it produces. And to be honest, I find it quite astonishing how that this actually works. That you can actually give a computer vision algorithm a 2D array of RGB values, and it produces a sense of depth out of that. There are issues with it. It's not perfect, not at all. That's also the reason we were a little bit cautious at that time. So like, okay, ship that, because we didn't think that that this will be first of all the end of the improvements, but also it's maybe not good enough for the high quality that you would expect in a grading room. Yeah, especially with details here. So I also picked like really hard shots just to also show the limitations of that. But then in January 2024, 4 years later, there was another model published, and that already raised the level quite significantly in terms of stability, in terms of precision. And this is something where we thought like, oh yeah, we can start to think about working with that. We can see it, over the 4 years there's quite a big improvement, I should say. So we kind of get a sense of the face and a sense of the hairs. Yeah, but then exponential growth. 6 months later, so we didn't need to wait another 4 years, but 6 months. There's a second version of that same model, and you can think of if you have a V2 of something, it's very much like if you would have a second version of a print film emulation. So like, oh, I've tweaked the algorithm a little bit and improved the measurements and the data, and this is now depth anything v2, which produces quite good results. It's not perfect, but we see the progress here. So I think this is where you said like, oh yeah, I'll take it, see how far we can get it. And then from June to October, there was another model which seemed to be very promising. That one is from Apple, Depth Pro, and on a still frame, it's really impressive. But at the moment, what we are fighting with, or what we are evaluating, is the temporal stability of this algorithm. So every algorithm has its strengths and weaknesses, especially when you see this here. There are some things that happen and which we need to mitigate when where the thing goes also horribly wrong. So while it improved some aspects, it decreases other aspects. So let's try something with that. So what I will do, go back to one by one. And this is kind of my one way of testing that. So what I do is I take a depth keyer. So that depth keyer basically allows you to take a depth map and then select which range you actually want to use, and then you can do a traditional color grading within that mat. And what I do is I want to change the lighting ratios of foreground to background, because I think we also have a lot of cinematographers here, and talking about lighting ratios of foreground background has some kind of relation to what we do all day, or you do all day. So what I do is on the background, I always make the background darker and the foreground brighter. For example, here I make the background darker by 1/8 of a stop, and I make the foreground brighter by 1/8 of a stop. So in total, it's 1/4 of a stop of change. And if we play this back, we can see that it looks quite okay. But also, we need to acknowledge that we are not doing that much of a change. So if we do now half a stop, so going 1/4 of a stop down and 1/4 of a stop up, we see, okay, it's also fine, but if we look a little bit more careful, we will start to see that outline that is basically produced by not exactly tracking the edge of that face, of that hair in this case. So, and if we go one stop, then that will probably not pass QC here. So we need to do something with that. So really, one key lesson is that the quality of the algorithm correlates with the amount you want to push. So if you need to push more, you need also a more exact algorithm, because if you push less, then it's just below the threshold of what is visible. If you go 2 stops, and then if you go 3 stops, you will see it's more like as if this would be a Zoom call, and not really appropriate for the big screen and the high quality thing. So we thought about this, and we saw this as a general problem with all of those models. So we thought about that. So one obvious thing you could do is you could try to blur that mat, right? So to get rid of the edges. But that does not really fix the problem. It just smears it out over a large range of pixels. So we made an algorithm which looks at both the mat and also the image. So it has basically 2 inputs. And then what it will do is it will look at the edge of the mat, at the gradients in the RGB image, and it will transfer the gradients of the image to the gradients of the mat. So if we do this instead, we can see that we can smear out that mat and actually make it latch to the actual edge of the different objects. So this allows us now to, if we go half hour, if we jump to 1 stop, And if you look closer here, and if I bypass this maybe, we can now utilize maybe not ideal matte, and we can just push it further. So now when we go like 2 stops, and again, and this is what I mean with like we take something that is not designed primarily for our industry, and then we add domain knowledge of our industry to it to make it appropriate for our use cases. And now if we do like 2 stops, so if I do before and after, that could work for that shot. And if we do 3 stops, now you see that we need to do more than just an exposure change, because now the flare levels also don't match. So you would need to start to also match the shadows and the flare level of that image to make the foreground and background sit more realistically together. But in terms of that edge detail, we can say like, oh, we can push that shot probably by 3 stops. Is this a general thing? Can we now go home and say like, okay, we can now light without any lighting ratios because we can push and pull by 3 stops? For this, I made this example here because it really depends. So if you have this image here, same thing. I use that depth map to separate the foreground and the background, and now I go half a stop, 1 stop, and if I do before and after, you can see the problem here. The depth map is not really getting the details of the hair. And here I'm using depth anything, the first version. We will come to the second version as well and see if this actually helps or not. And so here we would say, okay, we use the same trick. So we use that edge filter here, which does this transfer of gradients. So if we go from here and you will see that it basically transfers the actual edge of the foreground or from the RGB into the matte. So it refines the matte. We can maybe go to half a stop, and that kind of works. But even here, if I go to 1 stop, you see already kind of a halo-y, especially because the things are not moving. We are much paying closer attention to the details. If everything is moving, the eye has no chance to actually spot those errors here. And if we push this by 1 stop or 2 stops, while not having a hard edge, it still doesn't look that realistic here. And if I push 3 stops, then you see it does not work. So I would say in this case, maybe 1 stop of foreground-background chains using this technology alone would be, I would not go more than that. So you cannot really say that using these machine learning infused computer vision algorithms can allow you to change the lighting ratios of 3 stops every time on every shot. It really depends. Here what I have is the depth anything V2, and while this gives us here in that hair here, so if you look at here, so it understands the hair, but unfortunately it is not so stable over time. So while we have greater details, we have also greater variability, unfortunately. So while we get maybe that hair here, we see a little bit of more of temporal flickering. As you can see here, if I zoom in a little bit more, you can see that, this flickering here is introduced by that second version of that. So what would we do realistically in a grading session if we need to do that? So we would maybe utilize this computer vision algorithms to give us a stop or a third of us or 2/3 of a stop, but then we would look at it and would see, oh, there is also some artifacts down here and maybe here and there, and we would start to fix it using traditional tools, like for example, I could use an edge to limit the effect more to the top part to get rid of that, and then I would probably add another shape over here and just blend back the original and maybe add another one here and blend that back. And you would track it. I don't do this now. So meaning that you would use classical tools to, in combination with these new computer vision algorithms, to actually finish the job. You could use also face tracking, obviously. And now I'm adding a quick shape here, overall skin maybe. And now what you could do is we push this maybe by one stop, which will be probably too much. And we see a hard edge here. And I do this on purpose because what is also cool is that this edge refiner not only works with a depth map, but with any map. So what we can do is, if I crank this up, it will take the gradient of the actual image and will transfer it to the gradient of the mat. So this also works nicely with shapes. All right. So it depends. We have another technique which is called segmentation. So what we can do is, I just prepared this up here. We have machine learning powered tools that allow you to basically select, point to a collection of pixels, and then a machine learning model will try to understand the what that object, which pixels belong to that object, and that could also be used to change the lighting ratios. So what I'm doing down here is I'm drawing a box, and then it will look inside of that box and will give me a map of what is the highest probable object in here. And if you look at the mat, and this is why in all of the demos you see online, there's always a thick edge around the mat. This is because that is where all of those algorithms fail. And just we need to be aware of that. And so if I do the same thing here, going one stop or two stops, it really does not change the ability of what we can do. And with the mat tool trick we do here, we can improve it again, but it doesn't really change anything about how much we can push that job. Okay, so another thing. So we're getting now further and further down the line of computer vision algorithms that will hit probably interactive color grading. Is another one called trimatting. So trimatting is a technique where we take a machine learning model, and instead of training it to do the whole segmentation, we only train it. And with I don't mean myself. I'm not doing training myself here. But those models are only, all of the capacity a model contains is used to find foreground and background given a trimap, basically given a boundary. So we have a boundary here where we say, like, okay, this is the foreground, this is white, and then we have the background, this is black, and that model only looks at that area in between the foreground and the background. And it's all its capacity, its expressiveness, it can lead towards disambiguating in the area in between what is the foreground and what is the background. So we have all the computational power to only on the edges. And if we do this is what we get out of that. So going from here to here. And this is pretty amazing, I must say. And this gives us basically finer control over the edges. But it's also computationally much more expensive. But here we can now change the foreground and background. And yeah, I cached that strip, so it's not real time, but you know these little C buttons. Then that result is basically cached. But now we can produce really nice foreground and background changes. So now going back to that thing here, what if we do the same thing here? So what I've done here is I used a segmentation to give me a rough edge. Rough outline, and then I'm using some erosion and dilation and inside-outside blur to basically produce this tree map, and then I hand it over to that algorithm, and that basically gives me something like this, where I get lots and lots of details of hairs and so on. So if we do again that comparison here, we're getting much better in terms of the details, but unfortunately, in this shot, it still has problems with the temporal stability. So while it works really great on one shot, it might not work as good on the other shot. All right, so can we do something else with that? And now going really deep into the weeds, and this is more like a tech demo rather than something that you will see in the near-term future, because, spoiler, it's not ready yet. So what we can do is we can use computer vision to try to not only estimate the depths, but the whole geometric layout of that scene. And then we can use classical relight models to then relight the scene. I'll do this. Probably Bayside will explode now. No? Okay, good. It's pretty... so what we can do with that, and if I synchronize that scene here, what we can do with that is now what this thing has done under the hood is it has reconstructed basically this geometry of the scene and allows me now to add lights to that scene. And so this is both emulation, so we go from an image to a 3D scene, but then we switch over to simulation to do a standard relighting technique. And this is a real 3D relighter. We don't think that 2D or 2.5D relighters are worth to try. We just go all the way in. And what we can do is we can then basically place a light on her and try to relight that thing here as well. If we zoom in a little bit, it works. Good. So while this looks cool, if we look very careful, and this is the huge problem with all of the relight approaches we see also on those handy apps, is that the way skin interacts with light is not a simple shading function, but it has subsurface scattering and all sorts of complex interactions. And if we don't impose that on our relighting model, then, I mean, it makes a nice demo, but you can see that it immediately gives her a plastic feel, and that is something which we first need to fix. Before that we actually think that is useful in practice. But also what is the problem is that these models now produce several modalities, not only depths, but also normals, XYZ positions, and now we use computer vision to produce several modalities at the same time. So we're not only having flickering or temporal instability of one modality, but of several modalities in between. And so that means while it's nice that it reacts realistic in terms of the light direction, we can see that we have all sorts of interesting flickering and strange behavior on the face as well. While this looks like a promising technology, it's still a long way to go. But we are in an exponential growth. So my summary, and then we'll head over to the panel discussion. Trained algorithms. On the one side, we have computer vision algorithm. It improves what a creative can do, or make it more efficient, and improves how a creative interacts with a computer. I would say it makes it less technical. Algorithms do not provide 100% success rate, as I have clearly demonstrated in all of those examples. We have challenges with temporal stabilities and edge handling, and we are working on that. But we are in an exponential growth. On the other side, computer-generated imagery based on machine learning techniques. There are various technical and non-technical challenges, and it's more based on visual effects techniques and not so much on interactive color grading at the current state, and probably in the near-term future. And those projects need more grading than less. So overall, I want to end with a smiley, because overall, if I look into the future, I'm pretty excited about this new technology and what it enables us to do, be more expressive, and have more things to do rather than less. And with that, I want to ask you if any one of you has one question. Maybe we have only time for two, and then we are exactly at 1 hour. There was one there, and then one. You're not allowed to ask questions. You will ask. Okay.
So when we're talking about the temporal stability of these models, I imagine we have two solutions. Make every frame more accurate, or try to somehow stabilize the process across. So come in with a post-process and stabilize the temporal problem as a separate issue instead of like trying to make predictions of every frame better. Which is the way that we're trying to like make those improvements currently, and essentially would stabilizing the temporal issue over a few frames help fix the problem?
Yeah, that's an excellent question. I give you a beer tonight for that question. The answer is both things you mentioned are hacks. The real way of solving that is to give or to train models not on individual frames, but the whole body of images. So instead of basically trying to fix up the problems afterwards by improving the per frame model or fixing it over time, there are also trends going in that direction, is to have algorithms that look at 20 frames, 50 frames, or the whole movie, the whole clip itself, and will infer at once a modality of our interest. There are some challenges with that, is because you need some of those models. They need 20 GB of video RAM on the GPU, and imagine if you load in 200 frames, those models become really big. So this is at the moment a limitation. So I think we will, for a short while, deal with those hacks to fix basically the temporal issues of those rather frame-based or short time interval algorithms, but eventually at some point we will have a key breakthrough of efficient video processing, and at that point I think all of those temporal instabilities will go away in one go. So first 2 rows down. Yeah, perfect.
Yes, hello. Do you have any thoughts about using machine learning algorithms on color transforms? We usually get lots of these break-in LUTs. LUTs that just break are very badly made in let's say in early look development. A photographer comes in, gives us a very broken LUT. I sit down maybe, and now with Chromogen, with other tools, try to break it down to some robust transforms that actually can work on scene referred imagery and stuff like that.
Yeah.
Do you envision to have a way to kind of train on adapting a color transform that is broken, not completely matching it because it will still be broken, but to make that into robust tools?
I think we can do a lot with traditional algorithms to help you with that. Before we, it's always like you can, if you have a hammer, everything looks like a nail, right? So you see like, oh, now I've done something with machine learning, and you like throw it onto everything. But I think the problem of smoothing color transforms, there are other very interesting ways of fixing those or improving those transforms, which are not necessarily machine learning based. Yeah. So it's always like we don't need to use machine learning if there is a deterministic way of doing it with classical tools. And this is always what we really say. Okay, what is the task? What is the best tool for the task? And I think for that task, I don't think. Oh, I don't know. But I think there are other things we can try first before going into that domain. Okay, and there's the last question over there.
Hi, first of all, thank you for the talk. Who is doing this research and paying for it? Is it FilmLight or is it plugin driven?
Which do you mean explicitly?
Let's say, is it 3, the ones you showed?
Yeah.
Is it who is doing it, and so who is paying for the research? How is it going to work in terms of implementing in the software?
So we are using both self-trained model in, for example, the face tracker. That is something we have trained from scratch ourselves. And then there are open source foundation models that we use and build our tooling on top of that. So I would say the bulk work of training is done by typically research organizations that open source that the technology, that result, and then we bring it into FilmLight and then do a lot of integration work and make it fast and robust. And there's a ton of computer science considerations and computer engineering, how to get them fast, how to offload and onload them when you run out of the out of video memory. How can you get a smooth interactive grading session even if you're on a laptop, for example, as I showed this today. So all of those things are also very hard. Thank you.